All right, what's up, guys? So today I'm going to be working a problem for Hess's Law in chemistry class. Okay, so for these questions, we're going to be looking for the enthalpy charge. We're going to be trying to look for the enthalpy change for this reaction right here, right there. So first, we're going to just highlight the products in different colors, and then go and, well, highlight the problem in different colors, like each element. So we're going to do the 2 nitrogen in green, oxygen in blue, and the 2 N2O5 in a yellow right there. Okay, now we're going to just do that. Same thing, just over here now. All right, so we have a 2NO5 right here. Let me just highlight that right there. Oh, let's see if y'all can see that right there. Let me just highlight these and we'll be right back. All right, guys, we got these all highlighted and now we're back. So we have the N2 in green, the O2s in blue, and the N2O5s in yellow. All right, so now that we have those, now we're gonna isolate the problem that only has one, or the element that's in one problem alone. So let's just do the N2 first. So we see that we need 2 N2 on the reactant side over here in the problem that we're trying to get to. And we only have 1 right here. So we're gonna have to multiply this whole equation by 2, and we can leave it on this in this formula. We won't have to flip it because it needs to be on the reactant side, and it's on the reactant side. Okay, so now I'm gonna flip this and multiply it by 2, as well as its enthalpy charge, and we'll be right back. All right, guys, so you see this? So we did that. We didn't flip it, but we multiplied the stuff by 2. Oh, wait, hold up 1 second. Okay, guys, now we multiplied everything by 2. All right, so now that this is a 2n and that's a 2n, we're good for that for now. And our enthalpy charge got multiplied by 2, so now it's a negative 696.4. Negative. Let me put that negative there. So now it's a negative 696.4 kilojoules. All right. And now we're going to go to the N2O5. And since we need 2 of those, we're going to do the same thing we did to this problem, but here. And instead, instead of leaving it alone, we're going to have to flip it as well, because this NO2 is on the reactant side, while this NO2 is on the product side. So I'm going to write that down here, and we'll be right back. Okay, guys. So we went ahead and did that. So now that N2O5 is on this side now, and it's a 2 because we flipped it and multiplied it as the same where we did here. For the enthalpy charge, since we flipped this equation and multiplied by 2 for this to be on this side and with this amount. So we did this here, as you can see. Now it's a 153.2 kilojoules and it's positive. Okay, so now we're just going to leave these here, leave this one how it is. Actually, no, we're not. Yeah, no, we're not. All right, so this right here needs to move over to the other side so it could subtract from the other one. So we're going to flip this equation and not do anything else to it, but we're going to flip it for now. All right, we'll be right back. All right, guys, so we went ahead and we went ahead and did that. We flipped the equation and we didn't have to do any multiplication or division for that. All right, so now we're just gonna highlight the products, the things that we need, not the products, but like the elements that we need up here in this equation right here, and see what we have so far. And then we'll do subtractions to see if we can cancel out any extra things that doesn't need to be in this problem. All right. Okay, guys, so we went ahead and highlighted the things that we have up here, down here now in the same colors, in the corresponding colors, I should say. All right, so now we're gonna do a little bit of subtraction. Since we have same elements, well, same elements, same subscripts, and they're in the same state of matter, we can subtract them. All right, so first we have these 602 and this O2 right here. We need a 502. So we're going to subtract one of these from here to give us that 502. So we're going to write this new equation down here at the bottom. Now we have that well, not 602, but 502, right? And we have that 1, 2, and, well, that 1, 2, brother. Okay, that 1, 2, and 2, right? So right here by itself is same on here. So they're both on the reactant side. Forgive me of all this all around speech I'm doing. First time video, something like this. Please bear with it. And yeah, okay, so we have this 2N2 and the 2N2 right here. They're both on the reactant side, so we'll just bring this down. Now we have that 2N2 and a gas right there. And that yields our 2N2O5 over here, which is in the product side. And these were subtracted right here to give us that 5 for this side, right? Because they're like elements, same state of matter, and all that. And then we have this one lone 2N2 that we could just bring down. Now for the rest of this problem, we're gonna do some subtraction. So we have this 2H2 right here, as we can see. We can cross that out with the 2H2 on the opposite side of the arrow over here as well. That's why it's best to keep the arrows all lined up, so when it's time to go and do that subtraction, it'll be nice and easy. Now we have this 4HNO3 and 4HNO3 on here, so we cross those out. And then same with these last two H2Os, we can cross those out. And we pretty much got our problem set down here, which is the same as up here. And we did everything we needed to do with our enthalpies. So now we're just going to add all of these up, and it's going to give us the enthalpy charge for this equation right here, which is going to be our answer. So I'm going to go calculate that, and we'll be right back. Okay, guys, so we're back. So as we can see, we got 28.5 kilojoules, which is our answer for this reaction right here. This is going to be our enthalpy change or enthalpy charge for this equation or reaction. I hope this helped, and please forgive me for this all-around speech. And all right, yeah, like and subscribe. Thanks, guys.